welcome to Sunday's edition of Cracking the Cryptic, where today we're going to be doing a killer Sudoku, and that's all. So it's quite rare nowadays we do a killer Sudoku. We did an incredible puzzle by Philip Newman a couple of weeks ago, which was a very minimalistic killer Sudoku, absolutely extraordinary construction. And this is also looking fairly extraordinary. You can see the cages are entirely comprised just of numbers, the number 14. And that's indeed the puzzle's name. And it's by Fry the Guy. And this has a daunting, well, it has an exceptionally high rating on Logic Masters Germany. Indeed, a perfect rating, 100%. But it also has 5 stars out of 5 for difficulty. So I'm guessing it's quite hard. It's been recommended to us a few times. And people say that if you're a mathematician who enjoys sort of number theory, apparently this might be a very interesting puzzle for you. Now, yeah, I was all right at maths at that sort of school and university, but number theory sounds a bit complicated. Anyway, we'll see how I get on in a minute. I'll read you the rules. You can probably guess what they are. What to mention first? We've just ticked over our 4th birthday. Can you believe that? So it's 4 years since Mark and I started making videos on the channel. What a 4 years it's been. It's been quite bizarre for the world and for Cracking the Cryptic. But yeah, thank you very much to those of you who wished us a happy birthday. And seemingly to celebrate our birthday, the Urban Dictionary has just introduced the verb to goodliff. Look, here it is. This is the Urban Dictionary. Thanks very much to Codec for pointing this out. I think Aspartagus also noted this on Discord, but there we go. Definition of goodlive. It's a verb, the act of pencil marking all possible candidates in all cells of a Sudoku before solving. And there's even a little example there. I'm going to goodlift this Sudoku and hope to spot some patterns. I love that. I don't know how you get a word into the Urban Dictionary, but whoever has put that in, well done. It might be Detroit Buffalo, whoever that is. Anything else to mention? Yes, we're nearly at the 1st of September. 1st of September sees our Looney Tunes Patreon reward coming out over on Patreon. So if you're a patron of the channel, do check that out. Lots of puzzles themed around cartoon characters, as you might expect. And they're a lot of fun with some rather nice graphics. So we hope you're going to enjoy those puzzles. And also, when is it? Tuesday night, I have scheduled the next episode of my quest to complete The Witness. I'm looking forward to that. So Tuesday night, 10 o'clock UK time. That's when we should go live. Now, all that said, let's get on with 14. And I will read you the rules. So normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage. Digits cannot repeat within a cage. So that means those 4 cells there have to add up to 14, which is a common theme throughout this puzzle, and we can't repeat a digit. So what you can't do, even though normal Sudoku rules would seem to allow that, that would not be allowed in this puzzle because although those digits do add up to 14, unfortunately, you've repeated a 4 in the cage, and you mustn't do that, otherwise you'll get the puzzle wrong. Do have a go. The way to play, of course, is to click the link under the video. Now I get to play. Let's get cracking. Now, what do I know about 14 cages in killer Sudokus? I'm noticing actually they're not, I thought they might all be 4 cells large, but they're not. That one is 3 cells. Oh, that one's 3 cells. Right, okay, so I think all of them are 4 cells large, apart from these, which are 3 cells. Now, I do know something about a 4-cell killer Sudoku cage adding to 4. In fact, I know 2 things. I've just thought of another thing I know. The first thing I know is that if there's no 1 in a 14 cage, then that 14 cage would have to be 2, 3, 4, and 5, because the 4 lowest numbers that are not 1 do in fact add up to 14. Now, the other thing I've just realised I know is that a 14 cage never contains the digit 9. Well, a 4-cell 14 cage never contains the digit 9. And the reason for that is that if you try and put a 9 into it, the other 3 cells would have to add up to 5. But without a repeated digit, the lowest digits you could choose would be 1 plus 2 plus 3, and they add up to 6. So there is no 9 in... Oh, okay, so I was about to say... That means the 9 in row 4 has to be right in the periphery. But in fact, that cell scuppers everything, doesn't it? So these 3-cell 14 cages can have a 9 in them. Ah, column 3 then, maybe. In column 3, the only places you can have a 9 are those two places. And, oh, no, not quite. Let me just stare at this for a second in case we can find some sort of pattern with the 9s. 9s have to be in those positions in box 8. No, maybe this is not the way to approach this. I'm not actually seeing much at all. Okay. Wow, I have got no idea then how to start this. Because if I could get... How on earth do you make any progress? I have a horrible feeling that what we're going to have to do is to work out all the ways that you can make 14 in 4 cells, and then think about whether or not you can have, you know, it's tricky though. I'm sorry, I'm being very inarticulate, but that's because I haven't really got a clue what I'm doing. I'm trying to work out what's restricted. And the 14 cage, the problem with it is, if it does have a 1 in it, I think there are quite a lot of ways of making the other 3 cells add up to 13. Let me just count them. Maybe there are less than I think. So let's say that there's a 1 and a 2. And if these were 1 and 2, the other 2 digits would add up to 11. And they could be 3, 8, 4, 7 or 5, 6. So that's 3 ways we've got, plus the 4th way, which is 2 plus 3 plus 4 plus 5. Now if you do 1 plus 3, oh okay, so 1, 3, 4, 6 would be the other way. So there are 5 ways. So right, so each of the 14 cages is one of 5 different versions of itself. Each of the 14 cages is one of 5 versions of itself. So we've got... But the highest digit we could put into one is an 8. There's only one way of putting 8 into a 14 cage. There's only one way of putting a 7 into a 14 cage. There are 2 ways of putting 6 into it. Or is it 3? 1, 2, 3. No, there are 3 ways. So 6 is going to be the most prevalent digit in our 14 cage. I haven't even got a pencil mark yet, or a coloured cell or anything. Okay. So there are, okay, so maybe I've got to think about 1s then, rather than thinking about 9s or 14 without a 1. Maybe I've got to think about the only way you can't have a 1 in a 4 cell 14 cage is if it's 2, 3, 4, 5. Or maybe I've got to think about... Hang on, I'm getting very, very confused about how to even attack this. So... I've got to see the humour here, because it is actually quite rare for me to just sit here and not have a Scooby-Doo what to do. But this is not transparently obvious to me what I'm meant to be even thinking about. So, we can say that this is going to be a long video, that's what we can say. Because unless some sort of eureka moment hits me fairly quickly, I'm going to be here for some time. Do we... So let's just imagine there was a 1 in that, for example. It doesn't do anything. It just doesn't do anything if there's a 1 in that. Because the problem is that these shapes here, if we look at these 2 shapes, sort of Tetris shapes, aren't they? Nested together. But if I know something about, let's say I know there's a 1 in those 4 cells, it doesn't actually tell me that there's no 1 or that there is a 1 in these cells, because these 4 cells don't see the entirety of this box. That cell, actually, we could say that this cell couldn't be a 1, and that cell couldn't be a 1. But absolutely this cell could be a 1, and absolutely that cell could be a 1. So that is absolutely useless. What you need is to know that if there are 2 digits in here that you need to have in there, then you would be able to know something, because you'd know they had to go down. That's interesting. That's interesting. So maybe that's what we have to do. Do we have to... Is it... Hang on a minute. Hang on a minute. Let me do some maths. If we do... If you've got 2 14 cages, which is 8 different cells of the Sudoku. Right, okay, here is an obvious point. It's never possible for these cells to all be different. That's very obvious, because the numbers from 1 to 8, if you add them up, give you 36. So if we try and make all of those digits different, we can't make them add up to 28. Now, oh, I see. Right, okay. Right, this is something I had not appreciated at all. Let's do this again. But now, let's ask if it's possible that there is only 1. We've worked out that it's not possible there are no common digits between this cage and this cage. So let's colour that one in, and let's colour this one in. Now, we've worked out it's not possible for there to be no common digits in purple and green. There must be at least 1 common digit, because otherwise the 2 cages together would add up to at least 36. Now, what if there's only 1 common digit? If there's 1 common digit between them, then 7 of the digits would be different, and that means we can make those at a minimum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, which I know is 28. Now 28 plus the 8th digit, which is a repeated digit, and therefore could be a 1, is 29, but the point is, I think, that that is greater than 28. So in fact, every 14 cage that's 4 cells in this grid has more than 1 repeated digit. Now, okay, and let's take that further. So we've now worked out there's at least 2 repeated digits between every 4 cell 14 cage in this grid. Every pair of 4 cell 14 cages in the grid. And there can never be 3 repeated digits, because if there were 3 repeated digits, there would axiomatically be 4 repeated digits. Because if the 3 repeated digits added up to 12, for example, obviously that 4th digit would always be the same digit, it would have to be a 2. So there are either, in every one of these 14 cages, there are either 2 repeated digits or 4 repeated digits. Now, right, now I want to look at these again, because this is what got me thinking about this. This cell and this cell in the green 14 cage just cannot appear in the purple 14 cage. It's impossible, because they see the whole cage. This cell sees those 3 in its box and that one in its row. The same is true for this one. So these are not repeated in that cage, which means these are repeated. So they are purple. Right, okay, and that square can't repeat in those squares, so those 2 squares are the same. Oh, this is absolutely fascinating. So I'm going to get rid of these 1s, because those 1s weren't just me messing about, weren't they? So now those 2 squares out of nowhere are the same digit. Which means that digit's up there somewhere. This digit... Oh, yeah. now I'm going to look at this Tetris piece, because this digit, whatever it is, sees the whole of that cage. So orange is not in that cage, and purple is not in that cage either. Oh, this is ridiculously clever, because now, if you can't put orange and purple in this 14 cage, but you know every two 4-cell 14 cage share a digit, then you know that that domino there has to appear in this 14 cage. So 2 of these 4 cells are green. Now 2 of them are green. I'm wondering if we can conclude something about the other 2. So this cage here, we know it doesn't have greens in it. So it has a purple in one of these 3 squares and 2 other digits that are not green. But those 2 other digits have to appear in the 14 cage, because we know that every pair of 14 cages shares at least 2 digits. Yes, okay. So whatever the extra digits are, there's 2 extra digits in the stem of this L that are not purple. And those digits have to go in that 14 cage, and therefore they have to be in those squares. So these squares here are the same. Yeah, this is ridiculous. These 2 squares here are the same as 2 of these 3 squares, so we need more colours. I'm going to get rid of green there. I'm going to make those red. Is red going to show up? Maybe blue, actually. I'll make them blue. And then I know that blue is 2 of those 3 squares. Oh, see, the problem is I can't tell now that that's 2 squares. Do I have to make these blue and yellow or something, and then make that yellow? This is going to get By the way, if any of you are playing this and you don't know how to do the multicolour mode, what you do is you click that, the settings button, and then you go down to multicolour mode and make sure it's on, and that will help you. So, yes, this is okay though now, isn't it? Because now I've got lots of things. I've got roping amongst other things, because now I've got this green domino must go in that green domino. I've got a blue, purple, yellow triple here, which is repeated there as a blue, yellow, purple triple, which means those squares are, yes, a blue, yellow, purple triple. And when you get this effect happening in columns of a Sudoku, this is called roping. So we've got 3 cells here which are the same as those 3 cells, which are the same as those 3 cells. So if you imagine, what are these 3 cells going to be? Where are they going to go in box 7? They have to go there, which means they have to go there. So you get this stripy pattern going down the grid. And if you get stripy patterns going down the grid, do you know anything about the world, is the question. You know that orange is in one of those cells, and therefore orange is in one of those 2 cells. I'm not sure I want to pencil mark that. I may change my mind, but let me just think about this a bit more. Right. No. Well, I still may change my mind. I want to look at green again now, because what I can see now is that this green is not the same as that green, because if these were the same, you'd have to put green in one of those 3 squares, which you can't do, because we know that the shared green digits in this 14 cage are those 2 digits only, and not these 2, which are sharing with those ones. So those 2, I might need another colour here, I think. I'm going to do this. I'm going to get rid of that and put red. No, I've just done it wrong as well. What I want to do is I want this one cannot be the same as that one, so it's the same as that one, which means that one retains the right to be green. Now, Now what have we got? So now, every 14 cage has basically been dissected, hasn't it? Every 14 cage now is made up of a domino. Yeah, does this mean... Haven't we got lots of 7s here? Am I going crazy? Isn't that domino adding up to 7, that domino adding up to 7, and that domino adding up to 7? Yeah, well, yes, and another way of seeing that is to see the colours of this tetromino here. This tetromino is made up of orange and then a green, yellow, purple triple, which is the same as that tetromino, if you see what I mean. If I drew a cage over that, that would be the same as that cage in terms of its composition. Therefore, that adds up to 14. So, yeah, I'm not doing this in a very articulate way. Hopefully it's very obvious to people, but we know that, let's make red and green X. Now we know that red and green plus purple and orange is equal to 14. So let's make that y. X plus y equals 14. But we also know that x plus this domino, x plus z equals 14. And we also know that y plus z equals 14. So I think it's pretty clear, at least to me, that those 3 digits therefore have to be the same number. And the only way of making them the same number is going to be for them to all equal 7. So this domino adds up to 7. This domino adds up to 7. This domino adds up to 7. This domino adds up to 7 because it's the same as that domino. And we have lots of things going on which add up to 7. Right. And that is absolutely beautiful because now I've got a 7, 8, 9 triple in this column, haven't I? Because if all of those 6 digits there are parts of dominoes that sum to 7, they cannot include a 7 in any of the cells. So these cells here can't be 7s, 8s and 9s, and there's a 7, 8, 9 triple in the column. Bingo! Our first actual digits into the grid after 22 minutes. You can't put a 9 in a 4-cell 14 cage. So that means that digit can't be that high. Wow. Okay. Yes. Here's some more magic from Fry the Guy. This is brilliant. It really is. Whether this is 7 or 8, what are those digits? And I'm not talking in terms of colour here, I'm talking in terms of size. The answer is they're small digits. If this is 7, this triple is 1, 2, 4. If it's 8, this triple is 1, 2, 3. So these digits here are 1, 2, 3 or 4. Now, those digits we know are all parts of sets of dominoes that add up to 7 in 2 cells. So these digits are all 1s, 2s, 3s, 4s, 5s and 6s. So again, we can ask the question, where does 7, 8, 9 go in that column? And they go in those cells. Okay. Right. What does that mean? So this square here is 1, 2, 3 or 4 as well. Okay. Oh dear, and now I think I'm getting stuck. I'm not sure how I can do... How do we go forward with this? How do we go forward with this? The answer is, I don't know. Maybe I can do... Problem is that there's not very good communication between the cells I have identified as the same in terms of the whole of the right hand side of the grid. Oh, good. Oh, sorry, I hadn't noticed this. That pattern looks awfully familiar to me. Oh, wow, yes, look at this, on the right hand side of the grid, this is all the same. Those 3 14 cages are the same as those 14 cages, upside down, obviously rotated around 180 degrees. So surely I can just run all this logic in reverse. I think this means I'm going to have roping in these columns, although I might have got the which way round it is wrong there. No, I think that is correct. But do we have a way of linking the colouring of the left-hand side of the grid to the right-hand side? Or maybe we don't have to. Maybe what we've got to do here is actually try and work on the numbers 1 to 6. Because if I can prove... What's the equivalent of that digit? That digit. So that's a 1, 2, 3, 4, 5 and 6. And if that's roped, yes, here we go. Got something. So before we go and try and do anything complicated with colouring, let's just consider what we can say definitively about the size of some of these digits. Now, because the logic is identical on the right side to the left side, this digit is the equivalent of that cell. So it's in a pair of dominoes, in fact this domino here, which adds to 7. Therefore this square is a 1, 2, 3, 4, 5 or 6. Now, from the roping look, we know these 3 squares rope, because they're the equivalent of those 3. They rope to those 3 and those 3. And therefore we know this little square here is also a coloured square in a domino that adds to 7. So that's 1, 2, 3, 4, 5 and 6. Now look at row 3. I've got 6 cells which can only be selected from the digits 1, 2, 3, 4, 5 and 6, which means that these squares are a 7, 8, 9 triple. Now, these two are both in 3 cell. Right, well that's good enough, I think, because now these cells and that cell cannot be 7 or higher, can they? Because that's going to break the total of the cage. So these are also 1, 2, 3, 4, 5 and 6. That's a roped cell, so that's 1, 2, 3, 4, 5 and 6. I need one more in this row. Do we know anything about these equivalent cells down here? I don't think we do, actually. It's the equivalent of those two, but we don't have a cage to tell us the value of this. Oh, that's bobbins worthy. That really is. Okay. Right. Do I know anything more? I can't eliminate 9s from these. I can't actually eliminate 6s from those because 7, 6, 1 would be a valid fill. So, bobbins. Right, I fear what we're going to have to do here. I think I'm going to have to colour this side of the grid, and I'm going to ignore in doing this the left side of the grid. And then I'm going to have to try and work out whether the dominoes I create on the right somehow correspond to the dominoes I've created on the left, so that I can get a single unifying colour theory for this Sudoku. Now, how on earth am I going to do that? That is the question. Maybe rather than do individual cells, I do dominoes initially. Is that sensible? Because I know that that domino adds up to 7, and that's the equivalent of that cell. So let's make those a different colour to anything we've got so far. So this domino adds to 7. that domino adds to 7. Let's make that grey. I think I've used everything else that's likely to be useful. So that domino adds to, now that domino is the same as, is that the same as this domino? Hang on. Yes, it is. That's the same as that domino. So that domino and that domino are the same. So this domino here is interesting. Yes, okay, right, this is important, I think. What is the colour, apart from grey? I know it's grey at the moment, but I want to try and equate it with a colour that I've got over here. So what we can say immediately is that whatever red and green is, and by, oh yeah, I suppose just to fill in something obvious, which hopefully everybody's figured out, what we've got over here on the left hand side is 3 dominoes that add to 7 that are different colours. Now there are only 3 ways of making 7 in a 2-cell sequence. In Sudoku you've got 1 and 6, 2 and 5 and 3 and 4. So what we've got to try and do, or what I want to try and do, is to map these dominoes onto and give the greys some colour. Now, this domino, whether it's 1, 6, 2, 5 or 3, 4, can't go in the grey domino here. Because if this, obviously if that was a 3, 4 pair, you couldn't put a 3 or a 4 here. So this domino could not be 3, 4. So this one and this one are not the same. But look at orange. Orange is in a pair with purple. Now, neither of those grey squares can be orange, so this is not an orange-purple domino, which means it must be a yellow-blue domino. And therefore, that becomes a yellow-blue domino, and this becomes a yellow-blue domino. Now, this is just ridiculous. This red one is going to fix my black one, I think. Because now this cannot be this black shading cannot be a red, cannot have a red cell in it, so it's not red green, and we know it's not blue yellow because you can't repeat blue yellow in a box. So this one is orange purple, I think. Purple orange, which means this one must be red green. Which means that the roping implies that there's... Oh, this is where it's going to get horrific, isn't it? Because now I don't know. I know this square is the same as that square because of the logic we did right at the start of the video over there. But I don't know what this colour is, so I can't just fill in the fact that this is either purple or orange because I don't know. At least I don't think I do. Okay. I know these squares definitely include green and red, and these squares definitely include green and red. Ah, there we go, there's something. There's green-red looking at that square. So this is a green-red domino, precisely. And that means that square is a 1, 2, 3, 4, 5 and 6, but I knew that already from the roping, so that's not helpful. Okay. So one of these is orange or purple, but I don't know which one, and this is orange, or maybe I'll label that one as orange or purple, but I don't know which of them it is. Okay, alright, so what do we do next? We must be able to... Yeah, okay, here we go. I've got similar logic here with the green red here, which did this. this yellow blue is doing the same there. It's ruling itself out. So that square has become, oh, this is lovely. This is absolutely lovely. This has become purple because of this blue-yellow thing. And that purple sees that square, so that becomes orange, which means that becomes orange, and that becomes purple. Oh, my goodness me. Now, right, now orange. There are 4 orange cells looking at the middle of the grid. So whenever you get 4 of the same number looking at a particular box of a Sudoku, you should be able to fill in that number, and I must go in the middle, mustn't it? So this has become orange. Okay. And what now? Now we've got purple in one of those. Now we know orange and purple add up to 7, don't we? So if you put purple and orange together in this 14 cage, you'd know that was also right. Oh, this is such a good puzzle. This is such a good puzzle. Right, this is not purple, because if it is purple, those 2 squares add to 7. These 2 squares add to 7, which means they either have to be red. Well, you can see they can't be orange-purple. They can't be blue-yellow, because if this is a blue-yellow pair, that cell is impossible. And if this is a red-green pair, that cell is impossible. So you just can't put the purple here. The purple must live here. So these 2 squares add up to 7. Wow, okay. Now, I feel we have made amazing progress with this puzzle. Ah, purple now must go in there. Look, that might be interesting as well. In fact, this is the last cage that we have not investigated. So this cage needs to perform some absolute magic. That's green, so that can't be green. Oh, but one of these is purple, isn't it? It's not this. Oh, yeah, okay. So is this a naked single? A naked single red. It might be a naked red. I need to check this. We know from roping. Yeah, this has become purple, which means from the roping, this became purple. Which means there's a purple in one of these, but it's not that one. So this is not purple. There's a purple down here. Now this square is now red or green. Yes, okay. And I was just wondering how we disambiguate, how we worked out that this was green rather than this was green. But I do remember that's because we wanted to avoid those 2 being the same colour. So this is green, which means this is not green. So that's become red, and these are not red. Now, if we look at row 7 of the grid, we have 6 low digits. So we've got the sextuplet on 1, 2, 3, 4, 5, and 6. So those squares have got to be 7, 8, and 9. Now, what do we do next? We know one of these is purple, but one of them is not orange. And we know purple and orange add up to 7. Right, this is interesting. This means there must be a 7 or an 8 in here, doesn't it? Why do I say that? Well, it's because if why is it? It's because it just is, which is not a very good explanation. So let me try and explain why I think this is true. If there are no 7s and 8s in the 14 cage, then we know because of what we've been doing before, there are basically 3 ways of arranging the 3 14 cages that we've found that contain digits just selected from 1s, 2s, 3s, 4s, 5s and 6s. And those ways combine dominoes that sum to 7. So there are 3 ways you can make two cells add to 7, and we can pair them up in 3 different ways to create 3 of the 5 possible ways to add to 14. Now the other 2 ways that you can make cells add to 14 that we listed at the beginning were 8, 1, 2, 3 and 7, 1, 2, 4. So once you avoid a 14 cage having the ability to contain the 7 dominoes, which is what we've done here, you must be in a situation where you need the 7 or the 8 into the mix in order to be in one of those other combinations. So we now know there's a 7 or an 8 in here, which means there's no... Well, it means there is a 9 in that domino, which means that's not a 9. It also means that these squares here have to be low digits. I don't know if we know the colour of those. I can't see that we do. But these are low digits. So we've now got 1, 2, 3, 4, 5 low digits. We just need that one to be low. And we'd have 6. I don't know if we can tell that or not. Oh, but what I've just noticed as well is that haven't I got exactly the same thing going on with this 14 cage? It's got 1/2 of the purple orange domino in it, but not the other. So again, this domino has a 7, 8 or a 9 in it. Oh, it's not got a 9 in it. So this has a 7 or an 8 in it. I'm going to just label that up just in case we can work something out there. Those 2 squares are the same digit. These 2 squares are the same digit. Wow, it's really very surprising, isn't it, that we can apparently just resolve everything from this point. At least that is very surprising to me. This square now is in a cage. Oh, hang on a moment. Oh, this puzzle just keeps giving brilliant stuff, doesn't it? It keeps giving brilliant stuff. Right. There's a 7 or an 8 somewhere in this 14 cage. Once there's a 7 or an 8 in the 14 cage, the maximum value of this square is 4. Because if we add 4 to 7, that's 11. We've still just got enough room with a 1 or a 2 into the other domino to get to 14. If this was any higher, we would be broken. 7 plus 5 is 12. You can't put double 1 into the other cells. So, orange is low. But in this, if we do the logic here, purple is also a 1, 2, 3 or 4 for exactly the same reason. We're just looking at this cage rather than this cage. Now, if purple is 1, 2, 3 or 4, and it is, and this domino has to add up to 7, well, it must be a 3, 4 pair. And that is a big deduction, surely. 3, 4, 3, 4, 3, 4, 3, 4. That one has just become a 3, 4 out of nowhere. Now look at this row. That loses its ability to be 3 or 4. Sorry, I don't know if we can do any more than that. Possibly, but I don't immediately see how to. But that feels like a huge, huge deduction. 3, 4 means that's not a 3, 4. Oh, that's not purple. I can see that. So this one is the same as that one, which is a 1, 2, 5 or 6. Okay. So, what on earth do we do next? we've got 2 high digits in column 5. So I can't have too many more, and there are a few options for where that 3rd high digit could come from. Oh, yeah, hang on, look at this column. Surely that's 6 digits, and it is. That have to be, they're all coloured digits, so we know that the 7, 8, 9 in this column are all forced into those squares. That gives me a 7, 8, 9 triple in box 3. So these become coloured digits. It's very fitting on a day when we've discovered that Goodliff is in the Urban Dictionary for pencil marking excessively, that I am pencil marking excessively. Now look at this row, because I've got a sextuple on 1, 2, 3, 4, 5 and 6. Remember, coloured digits have to be 1, 2, 3, 4, 5 and 6, so that's a 7, 8, 9. That means that square also achieves the goal of being a 1, 2, 3, 4, 5 or 6. One of those is a 9, so that's not a 9, just using the fact this is a 7 or an 8. Oh, hang on. Hang on. I can just place 9 here. Right, how did I get that? Oh, I see. So once I worked out that 9 couldn't go in this 14 cage and had to be there, it rules itself out of there. It could never go in a 14 cage there. So we have our first digit. It's a 9 there. This is not a 9. That means 9 in this box is in one of those 3 cells. And 9 in this box is one in this domino here. And that, I fear that may be as far as that takes us. You rotten thing. Ah, dear. I thought that might be good, but no, it seems not. There's definitely a 9 in this domino. Do we know anything about those 3 cells? You definitely can put a 9 in a 3-cell 14, so I don't think we do. So we're going to have to find something else about this puzzle that's going to help us to break it open. What is that thing? I don't know. I don't know is the short answer. These squares here, am I going to really do this? Am I going to label these 1s, 2s, 5s and 6s? 1s, 2s, 5s and 6s. Oh, that one is blue or yellow. Well, blue and yellow can't be a 3 or a 4 because we know that 3 and 4 is only in orange and purple. So that's dropped down to being a 1 or a 2. That means its counterpart must be a 5 or a 6 up here. But that doesn't seem to connect anywhere, does it? So that's a shame. But that means that there must be an orange in one of those 2 squares, I think. Because we know that there's a 3 or a 4 in this 14 cage, and that 3 or 4 is in that domino. So there's an orange in one of these, which means there's now an orange in exactly that square in box 1. That feels like a big breakthrough as well. That means that orange in this box, we know, or yes, this is good. Orange is not the same as red or green, so orange is there, which means this cell is also restricted to 3 or 4. Now we've got a 3-4 pair here. We can remove 3s and 4s from those squares, and that square as well. We've got a 3-4 pair in this column. So orange is in this domino in box 9. Now, what we might need next is a bit more. Somehow, some way, one of these 14 cages is going to have to tell us what the colour, whether this red-green is 1-6 or 2-5. No idea how that's going to happen. This 14 cage here, it's got a 3 or a 4 in it. It's got a 7 or an 8 in it. So the other digits it's got in it are low digits. They're 1s and 2s. Aha. This is big. This is big. Let's think about this cage. Let's put the minimum here. Minimum here will be 3. The minimum high digit would be 7. That's 10. That means the other two digits add up to a maximum of 4, which means they must include, well, a 4 would be a 1 and a 3, but we know that there's not a 1 and a 3 in here, as well as the 3 we've just put in. So there must be a 1 and a 2 in there. There must be a 1 and a 2 in there somewhere, and that means that square's not a 1 or a 2. Right. And I might be able to pull that same trick off down there. No, I can't. Oh, no, yes I can. Yes I can, because it's got a purple in it. There's a purple in this, along with... So it's the same logic, exactly the same logic. 7 plus 3 is at least 10. The only way of making up the remainder is going to be with a 1 and a 2, because you can't repeat the 3. So this has got a 1 and a 2 in it as well. That means there's no 1 and 2 here, and it's got purple in it. So there's a 3-4 pair there, which means that's not 3 and 4. We've got a 5-6 pair out of nowhere in this column. That means that's not a 5 or a 6. And it's not a 3 or a 4, just noticed. This is a 1 or a 2. Wow. So this is 1, 2, 7 or 8, and 3 or 4, depending on which way round it goes. This became a 5 or a 6 as well, didn't it? So maybe I've got to think about that. Because surely I can't have a high digit here now. The minimum of those two digits is now 12. So this is a 1 or a 2. Now I've got a 1, 2 pair in this row and box. So that square's not 1 or 2. That square's not 1 or 2. Which means that square is 1 or 2. Wow. Okay. So whatever that is going to have a friend here. I've got to be careful here actually. This pencil marking is not helping me. I was thinking I had a 1, 2 pair here, but I don't, do I? I was going to try and do something with that one as well. I think this logic is still alright. Whatever this square is, you're going to have the 1 or the 2 in this 14 cage is in this domino. And we know that this 14 cage in the middle box has a 1, 2 pair in it. So that square is also the same. So these two squares are the same digit, which means this square is not a 1, 2, 7 or 8, it's just a 1 or a 2. And those two squares are the same. Now this one, I don't think we can do the same magic with, can we? Because we don't know which of these is a 1 or a 2. We know one of them is, but we don't know which one. No, we do now. Oh my goodness me. Oh, good grief. This is so brilliant. Look at row 4 now. I hadn't realised that this square, I haven't coloured it, but it does deserve a colour because it's a 1, 2, 3, 4, 5 or 6. So there are 6 cells in this row that are low, what I'm calling low digits. So this square, and this square are a 7, 8, 9 triple. Now, oh my goodness me, now I've got a 7, 8, 9 triple in column 5. So that means those squares can't be a 7 or 8. The 7 or the 8, the 7 or the 8 is in this domino. And this is a 7, 8 or a 9, so this square's the 1 or the 2 in this in this 14 cage. Now that means those two squares are the same digit. Oh, right, okay. That's the simple way of now viewing this is where do the 1 and 2 go in this box? And they're not in those squares. So that's not 1 and 2. The 1 and the 2 must be vertical here. Therefore, they are not purple because purple is a 3 or a 4. But they do deserve colours. But eventually what we're going to have to do is to tie these to reds, greens, blues and yellows. Now this is a 7 or an 8 and a 3 or a 4. How do we resolve this? I think we're really, really close to understanding this puzzle now, after nearly an hour. I hope I haven't been missing things. This has been absolutely brilliant for me. That time has flown by. I've got a 7. Oh no, I already knew I got this. I've got this. So these are all low digits. Right, okay, that's nice. Let's look at this column. These highlighted cells are all low digits because 7, 8, 9 have gone. But this square can't be a 1, 2, 3 or 4. So that must be a 5 or a 6. Then I've got a 5, 6 pair in the box. So now those squares have got to be my 7s, 8s and 9s. Oh, I see, look. And now I've got a 7, 8, 9 up there, which gives me a triple in that row. So there's lots of colouring I've not been able to do yet that somehow is going to have to get resolved. How do I resolve this? This square is a 3, 4, 5 or 6. But we don't know which it is. And somehow maybe these cages, hang on, oh no, that can still be a 6 because that could be a 7 and that could be a 1. That would put a 1 here and a 1 down here. Ah, that can't be a 9 anymore because we're adding at least 5 to it, so that is a 7 or an 8. Okay, that's good. We know there's a 7 or an 8 here, there's a 7 or an 8 here, so the 9 in the column has to go there. And that gives me another digit. And that places... Oh, I was about to say that places a 9 in one of those two squares, but I'm not sure it does because this square seems to have the ability to be 7, 8 and 9 as well. Why did I pencil 9s into just those two cells? That is mysterious. I definitely don't trust this. So I'm going to delete the 9 from there. That seems good, but I'm not sure why this can't be a 9. If I've missed a point there, forgive me. I just can't remember. So in this column now, we haven't got. We've got the 3. We've got the virtual 3, 4 pair because this is down here. The purple 3, 4 pair, purple orange 3, 4 pair, 1, 2 pairs. So is this square a 5 or a 6? Is that what we're learning? I think it is. So right. Whatever the modern word is for eureka, I am uttering that because there we go. There we go. I've got it. I've got it. This square is not a 7. Why is it not a 7? Well, it's because of our love of 7s that has come to fruition in this puzzle. Because if this is a 7, this domino adds to 7. There, I've said it. But also, because of our colouring, that domino will add to 7 because that digit and that digit are the same. Well, if those two digits add to 7, we should be able to colour them in. Not in grey or black, but we should be able to colour them either orange-purple, well they can't be orange-purple, they see orange-purple in the row, or these two squares would need to be red-green. Well, they can't be red-green because then this square could not be red or green, or they'd have to be blue-yellow. Well, if they were blue-yellow, this square would have no fill. So these are not adding to 7, and if these are not adding to 7, these are not adding to 7, and therefore this square must be an 8. QED. That is just that is just mind blown. Whatever the emoji is for that is what that is. That's now not an 8. Now this is massive. This is massive. Now this has got to be a 7 and a 4. So this is a 4-7 pair. Now we know that purple is 4. Therefore we know orange is 3. 4, 4, 4, 4, 4. We know those two squares have got to add up to 6. So they can't include a 6 in them. That's a 5 and that's a 1. Now that's a 1 and that's a 2 and that's a 2. Ah, this is one of the most brilliant puzzles. Honestly, it's just ridiculous. That's a 6. That's not a 6 anymore. Okay. And we can take a pause for breath. Now those two squares are interesting, look, because they have to be 2 and 6, I think. Which actually doesn't, well, it means that's not a 2 or a 6. Oh, I see, so that's going to be a 1 or a 5. But we still don't know the orders of the red greens and the blues yellows. So we've still got work to do there. That square's not a 3 or a 6 anymore. But do we know, these have to add up to 12, don't they? Because of the 14 cage, so that's going to have to not be a 9, that's going to have to be 7, and that's going to be 5. Therefore that's a 6 and that's a 1. And therefore that's a 6 and that's a 1 and that's a 2 and that's a 5. And we have learnt the parity, or the versions of 7 that we've got in the other thingies. So this is a 1, 6. This is a 2, 5. We haven't managed to work that out, but we know that's a 1, 6. This 7 is giving us a 9 here. That gives us a 7, 8 here. That means this is a 9. That means this is a 9. So the pencil marking earlier was mistaken. Now we've got to put 9 here. We've got to put 9. Oh, it doesn't look like we're quite going to get the 9s done. Oh, yes, we are. That square's got to not be a 7, so that's a 9. That's a 9. And that's a 9. There we go. And now that square's a 4, just to complete its box. 5 here means that square's a 6, that square's an 8, that square's a 7. I really, really, really hope this keeps going, because this is such a clever puzzle, and it would be just magnificent if it can appear on the channel. Now 1 is ruled out of those. Now 4 is purple, isn't it? So actually we can now recolour some of this. 4 is purple, so that's not purple, which means this is a 2, 5 pair, and we know the order. So that's a 2, that's a 5, that's a 2, which means it's going to get its own colour, or 2 colours. I've not differentiated between the colours here. Now these squares here have got to be 8 and 5 bobbins. That doesn't seem to be resolved. But this 2 will resolve it. 2, 5, 5, 8. That one gets its colouring now. That one gets its colouring. 6 must get some colouring. Yeah, that's sort of a red-green effort, isn't it? That one gets its colouring. Now, where do we go from here? This looks like it's another chromatic masterpiece, isn't it? Well, this is a 2-5 pair, and there's a 5 here, so that must be a 5, and that's a 2. And then in this column, you need a 3, which is there, and therefore that 3 should be orange. Oh, this is working. It's just working, isn't it? Now, this has got to have an orange, and it can't be that one anymore. So that should be a 3. That's not a 3. This 8 is giving us this digit. Now in this row, what do we need? Is it 6? I think it's a 6 into that square, which is resolving the colouring of my 1s and 6s. This 6 has now become a 5. That's become a 2. That can't be a 4 because this has to be a 7 or an 8. So that's a 1, that's an 8, that's a 7, that's a 7, 8, that's an 8, 7. We need an 8 in that box. This has become an 8. This has become a 5 and a 6. This has become a 1 and a 2. Don't know if that 4, 7 is resolved. This should be a 1. And we need 4, 6s, 7s and 8s. So this is a 4, 6 pair, and we can do the order. 6, 4, 8, 7, 7, 4. And I think I'm going to just click tick. Yes. Wow. And then now I know I've got to correct a whole load of the colouring. So let me just do that, because I know people get frustrated with me if I don't do it. So that square, look, that's got to become red. Oh, hang on. That's gone wrong. No, that's got to be green, I should say. 6s are greens. So every 6 in the grid needs to have a green flash, which means that one loses its green. This one gets its green. All of the so these 1s lose their black tag and they become red. And we can fix these as well, and I'm going to do it. So now we need reds in those 2 squares as well. That's got to become 2 of it's becoming its flashy yellow and blue, isn't it? So now all the 7s, 8s and 9s should be uncoloured, and they are. That 5 needs a bonus. When I miss them, all the comments are just about the colour I've missed, so I apologise. That one, these 2s as well, I've got to have their colouring like that. That might be correct. I hope it is. And I just want to say a huge thank you to Fry the Guy for one of the most brilliant puzzles. I mean, every day at the moment we're doing these incredible Sudokus. This was pretty hard, surely. I don't think there was another way of doing this other than incredible amounts of colouring, because at the start I couldn't see what to do at all. And eventually we managed to work out something up here, didn't we, which gave us a very tiny beginning. And from there, every deduction was hard earned. But in the end, you can actually fill the grid uniquely. It is just a stunning logical masterpiece. It really is. Fry the Guy, take a bow. I'm so sorry for taking up so much of your Sunday evenings. I hope you enjoyed it. If you have stayed with me to the end, do let me know in the comments. I do enjoy them, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic.